Hey guys, and welcome back to the channel. For those of you who are not sure, I'm Jordan. I'm the one who has no life, as evidenced by me recording this at 5 p.m. on a Friday. So today we're going to be talking about one of my favorite databases, Percolator. Actually, sorry, that was a typo there. We're talking about every rapper's favorite database, Percolator, and let's go ahead and get into it. Alrighty, let's go ahead and get started. So today we're going to be talking about a system that came out of Google in the early 2010s, known as Percolator. So basically, the main idea of this paper is that they want to be able to incrementally crawl certain web pages, right? A new web page comes around, they want to be able to go ahead and put it in their search index for Google and returning results on it. And so ultimately, the impact of this system is that they're able to reduce the average age of documents in their index by 50%. Now, the reason they're able to do that is because this effectively allows them to process documents as they come up rather than in a massive batch where you have to process every single document in the web at once. And so we'll talk about why that is in a little bit. Ultimately, Percolator is just a wrapper around Bigtable, so it will help if you've watched the Bigtable video and similarly the GFS video, because otherwise we're going to use some concepts that we haven't yet discussed. So let's go ahead and talk about it, because ultimately what they're doing is providing a bunch of multi-row distributed transactions. Cool. So let's go ahead and discuss the need for Percolator in the first place. What was Google doing before the system came about? So basically, in order to even discuss that, we first need to discuss how web indexes work. So a web index, or a search index in general, built on crawling the web, is going to work something like this. So let's say I'm page 1. Okay, this is one website, and it has a link that forwards to page 2. The link is basically going to be stored locally to the data of page 2 in your index, right? So, your index is just effectively a database. You've got a row for page 1, you've got a row for page 2, and then page 2 is going to have some section in its row that says, hey, here are all the links that are forwarding to me, and one of them is going to be from page 1. Now note that right off the bat, let's say I'm crawling page 1 and it's got 10 different links. Now I have to write to 11 rows, right? Because 1 for page 1 and then 10 to the 10 different places that those links are pointing to. And so all of a sudden, if we want this to actually be an atomic write and we want it to be a serializable write, we may need ourselves a distributed transaction. It wouldn't be distributed if we're just writing to one single node, but if we're writing to many different nodes for all of those rows, this is going to get more complex. Number 2 is URL clustering. This is another concept that I want to cover. So if multiple links are going to actually hold the same content, we only want to show the one with the highest PageRank. So PageRank is an algorithm that Google has where it basically comes up with a score for each page based on how many links are referring to it, right? So the interesting thing here is that, as we covered in our web crawler video on this channel, basically there's a lot of duplicate content on the web, and we'll typically figure out whether one thing is a duplicate of another via a few different things. Maybe one of them is something like taking a hash of the content. But the gist is, if we have 2 websites that are duplicates of one another, and then you've got 2 other websites that each have one link forwarding to each of the 2 duplicate websites, ultimately the forwarding links are only going to be stored with the duplicate with the highest PageRank. And so again, that is another reason why, if you're indexing a new website on the fly, you don't want it to be the case that as you're performing this indexing, if other web pages' page ranks are actively changing, we want to basically be able to make a serializable write. Otherwise, we may see some inconsistent state of the database, and this is going to be problematic. We're going to have to deal with some race conditions. Cool. So basically, let's talk about now what Google was doing before Percolator. Before Percolator came about, every single time that they wanted to add new documents to their index, they would basically have to run an entire MapReduce job that would crawl the existing repository of all documents in addition to the new ones that they're trying to crawl, right? So basically the way this is going to work is we have a few different MapReduce jobs that we chain together. First one is going to compute that PageRank, right? We go through all of the links that refer to a page. This is a linear scan ultimately, and basically a shuffle, and then ultimately a reducer function. Then we go ahead and use the actual content of each page to compute duplicate clusters. And then finally, we can do the link forwarding, right, where we assign to basically every single website based on the highest scoring page in a particular cluster. And so each of these steps are going to be run completely sequentially. So the problem that I mentioned before was that the page rank of a page could in theory change while we're doing our link forwarding or something, right? Well, that's not possible with MapReduce, because the way that MapReduce jobs work is that when you're chaining together MapReduce jobs, you wait for the first MapReduce job to finish completely before doing the second one. And so, for example, you're not going to compute your clusters until the PageRank MapReduce job is completely done. And so as a result of that, it makes things very easy to reason about. We don't really have to worry about any race conditions in this pipeline. At the same time, we've got a big downside, which is that it requires a complete pass of all of the web pages to compute. So let's say I only want to look at 2 new websites and add them to our index. Too bad, you have to go over the entire data set. And that is going to be really problematic. It basically means that the documents that we do see in our index, on average, are going to be a lot more stale because it's a massive data set and it takes a while to run these MapReduce jobs. So again, the kind of problem that we're trying to address here is how can we do incremental processing of the web? Cool. So let's talk about life with Percolator, right? We create this system that allows us to do these incremental multi-row transactions. What does it actually afford us? Well, basically, let's say we've got a few new web pages that we want to crawl. Basically, we can just go ahead and use transactions, right? And those are going to be atomic and serializable. So when we take these forward links and we compute them, and then we ultimately write them to other rows, we can do first a read on all of the other rows that we're writing to ensure that all the rows that we're writing to are still the rows with the highest PageRank score in their duplicate clusters. And this is going to allow us, by basically ensuring that the predicate of our reads have not changed, to really simply reason about our table. So again, pretty simple stuff, which is very, very nice. And we just go ahead and get it done. So how do we actually implement these ACID transactions? Because that is going to be the nature of the problem here. Let's go over the high-level architecture. So like I mentioned, this video is kind of highly coupled with the big table and the GFS video. I don't really think you have to completely understand the inner workings of either. I think it's enough to understand that GFS is basically a distributed file storage system. Bigtable is a database that's built on top of that only supports single row atomic writes. And then Percolator tries and extends that to multi-row writes and doing them atomically and serializably. Cool. So basically the way that it works is if you look at this guy over here, on one single co-located server, we might have our Percolator worker, we might have a Bigtable tablet server, which is basically responsible for a few partitions of bigtables. And then we've also got our GFS chunk server, which is really just holding the SS tables that are the underlying columns of a given bigtable. And so again, Percolator is really mostly just going to be wrapping calls to the Bigtable API with some additional logic, and we'll talk about some of the additional logic that it ultimately performs. Another thing to note is that at the end of the day, Percolator is going to be built for very high throughput. So I'm going to discuss some things in this video where you're like, what in the ever-living fuck are they doing? That is slow as hell. And I agree with that. That being said, these are not human-triggered writes, right? This isn't like you going to Amazon.com and trying to make a purchase and being pissed when that takes 30 seconds. It's okay if it takes 30 seconds because the MapReduce job takes a whole lot longer than that. What they really care about is that, maybe there are 1,000 web pages to go ahead and index. We want that aggregate number to be relatively small, but for every single one of them, it's okay if an individual write is fairly slow. Okay, so one thing to note is that Percolator is going to implement snapshot isolation. And kind of, I guess I would say Bigtable does as well, and Percolator kind of just inherits that as a result, in the sense that Bigtable is able to store all values with a timestamp field. So just as a quick refresher on what snapshot isolation allows us to do, by having this timestamp field around, you can pretty much always make a consistent read of the database. So let's say that I were reading these 2 rows right here, right? Jordan and Corinna, and they hold basically the current balance of our bank accounts. Now, for whatever reason, I'm making a $5 payment over to Corinna at time equals 10. I wonder why. The gist is, let's say I were to read this row over here at t equals 9, right? So then I see that at t equals 9, Jordan has $10. And then because this is a long-standing database read, it's going to take some time for me to read over the whole table. Maybe I finally get to the row Corinna at t equals 10. And so at t equals 10, notice that the Jordan to Corinna balance transfer has gone through, and she all of a sudden now has $10. And note that now it seems like there's $20 in the whole system when the reality of the fact is that the combination balance of our accounts is only 15. So we read from an inconsistent state. And so snapshots are going to allow us to ensure that we always read from a consistent state, right? Because when I make a read, basically that read has a timestamp, and I can ensure that I only see data that has happened at times equal to or less than my read timestamp. So if I'm reading at time equals 9, even though this t equals 10 write may be there, in my case, I'm going to basically ignore that and then say, okay, Corinna still has $5 at t equals 9. Now, as far as Percolator goes, using these timestamps, it's able to do a little bit more than that, right? Because it can say, ooh, actually, if I'm reading at a certain time and then I see a write come in that's at a later time, perhaps I know that the premise of my read has changed, and if I'm writing based on that read, now we're going to have to go ahead and abort this transaction, right? It's doing kind of an optimistic concurrency control there. Cool. So what do Percolator transactions ultimately look like? Well, keep in mind that we're basically going to assume that every row is on a different node here, but effectively we're just using two-phase commit, right? We're going to have a prepare phase on every single row that we're writing to, where we try and establish locks on each row. And then after that, once we establish these locks, assuming that we're able to grab all of them, we will basically try and go through with this transaction. So again, if we're just writing to the rows Jordan and Corinna, at t equals 1, we've got committed writes with $5 for the both of us. At t equals 2, I basically grab a lock because I want to do a multi-row transaction. The reason we need these locks is that we ultimately want to make this atomic, right? It's not acceptable that one row might go through and the other wouldn't. And so right now we're just specifying, talking about the atomic piece, and then we'll talk about the serializable piece. So I grab this lock. Basically, notice this piece right here. Each lock actually has pointers, right? So in this case, the lock is pointing to itself, and we'll touch about why we do this in a little bit. But the reason why is this is called the primary lock of the transaction, and so we'll discuss that in a bit. So this is an uncommitted write now, and we're basically saying at t equals 2, Jordan is, we want to write that it's a $0 value. We have our lock set up, but we haven't written it yet. And Corinna, we still haven't been able to write the lock there just yet. At t equals 3, we set up the lock on the Corinna row. We have our newly proposed value. We know that it's uncommitted. And then also our lock is going to point to that primary lock. Every single other lock in a transaction that is not the primary is also pointing to the primary lock. At t equals 4, what we can actually do is go ahead and commit the write, right? So we start always by committing first our primary lock. So we commit this. Notice that now our value is committed. We don't have a lock in this cell anymore at t equals 4. And our data in the row Corinna is still uncommitted. And then finally, at t equals 5, we can commit that guy. Cool, so that's going to keep everything atomic insofar as, we need to be able to grab all the locks, ensure that we can make all of these writes. And then once that we have ensured that, we can then go ahead and actually go into our second phase, which is the commit phase, where we actually write them all. Cool. So basically, every single transaction is going to get a timestamp, right? And so I guess the gist of this is, if I'm a transaction and I want to, read some data and then ultimately write it, if in the process of that I see a committed write, big emphasis on the committed part, because if it's an uncommitted part, or if it's an uncommitted write, that means it may not have gone through. If I see a committed write after the start timestamp, I am going to abort. Very simple. Similarly, if I see an active lock on any of the rows that I'm reading or writing, I'm going to abort, because it means that another transaction is in progress and I'm about to write. So hopefully a pretty simple mechanism to actually go ahead and figure out whether or not we should be going through with our transaction. Cool. So there are a few kind of nuances to this whole process, and we're going to talk about them right now, because the above is basically really nice for maintaining serializability, right? This whole piece is saying, hey, if I'm T1 and I want to write to this row, but T2 has already grabbed a lock on it, nope, I'm aborting. Maybe I got a lock on it, but there's an uncommitted write, and then all of a sudden that write commits. Nope, never mind, got to abort. And so that basically ensures that we know that one of these transactions always went first. You're not going to have any interleaving of writes, which is nice. Cool. Next, we're going to be talking about client failure and deadlock detection. So the problem with two-phase commit, fundamentally, is that it is coordinated by a third party, right? So in this case, it's the client. If I'm the client, and I want to write to 2 rows, row 1, row 2, the first thing that I need to do is grab locks on those 2 rows, right? So we do that, we do that. Now, during this time, no one else can write to them. That's pretty important. And frankly, no one else can read from them either, because we're basically saying, we're not doing like a 2-phase locking here. We're basically saying, I have this lock, no one else can interact with this row. That's not going to work out. But what if my client goes down, right? Now no one else can interact with those rows, and those locks are never going to get cleaned up. So we effectively find ourselves in a situation where these rows become untouchable. So how do these actually get cleaned up? Well, it's not so simple, right? So let's imagine the following scenario. Same idea, we have a client, and it's writing to 2 places, row 1, row 2. So first we start by grabbing the locks. Then, right after we grab those locks, before we do anything else, we have a long garbage collection. So let's say this is a 30-second long garbage collection, and another client comes along and says, hey, I've seen these locks sitting here for 30 seconds. I think I'm going to get rid of them. So it starts by removing the lock over here on row 2. We remove this lock, and then right before we can remove the one on row 1, this guy over here comes back alive, and it says, hey, I want to commit now on row 1. So this is going to go through on row 1 because he still has the lock, and it's going to fail on row 2, and then all of a sudden we have a partially committed transaction, which is not cool. So we can't have that. Basically, the idea is if we allow other clients to remove our locks, we could end up with a partially complete 2-phase commit. Now, what some systems will do to avoid this type of situation is they'll have some sort of global deadlock detection system. And ideally, that's basically going to consistently ping clients and try and get a sense of whether they're alive or not. But basically, we don't do that in Percolator, right? We basically do this lazily. We allow locks from aborted transactions or transactions where the client basically went down to stick around until someone else wants to access the row. So this is known as lazy lock removal. So basically what we're going to do is, in order to avoid the situation that I cover over here in part 2 where we have this kind of conflict, what we're going to do is have a primary lock. So this is what I covered before, right? Every single lock besides one is going to point to a primary lock. Why do we do this? Well, basically it's going to ensure that when one client that is not the original one doing the 2-phase commit tries to remove a lock, it always starts by removing the primary. Similarly, every single client that is writing a 2-phase commit will always start it by writing the primary first. So what does that accomplish us? Let's say we're in the same situation as before, right? This guy has a long garbage collection after grabbing those 2 locks. This guy tries to remove the lock on node B. But it's going to see, hey, the lock that I'm about to remove is actually not the primary. In fact, it has a reference to the primary lock over here at row A. I have to go remove that lock first. So we're going to now try and remove the lock at node A. What's going to happen first is, keep in mind, I said when a client goes ahead and tries to complete its 2-phase commit, it always starts with the primary lock. So regardless of what happens in this garbage collection, either this guy is going to commit A first, or this guy is going to remove the lock on A first. And once that happens, basically once that A lock either gets committed or removed, it means that if it gets committed, the transaction has to complete because no one else can remove that lock in the future. And if it gets removed, it means that that transaction can't continue because remember, that has to be the first row that gets written in this 2-phase commit. So by basically synchronizing on this one single A lock, we guarantee that we can safely either remove a lock or commit the lock after any amount of time, which is really, really nice. Another nice piece of this actually is that now we can roll forward writes. So let's say the client does in fact commit this write over here, right? The client wins, it comes back from its GC, and it commits the write to the primary. So we commit over here, and then maybe it goes down forever. So this guy eventually is going to, the client on the right is going to say, hey, I want to write to row number 2. But, ooh, I see there's a lock on it. Let me go check the primary and see if that's committed. Oh shoot, the primary has committed. So now what I actually need to go ahead and do is commit this row over here before I can write any further. So we're going to commit this uncommitted write, which is good because in our 2-phase commit semantics, once any of those writes has been completed, all of them have to be completed. So this is going to allow other clients that were not the original one to actually help complete that write if the original goes down. And then from there, instead of removing the lock, this guy completes the write and then he can do his own write 2. Cool. So hopefully that makes sense. The main idea here, which I think is pretty interesting, is by using a primary lock for your two-phase commits, you can basically guarantee that other clients can remove that primary lock before you're able to write to it, thus aborting your transaction. Cool. Let's go over a few more serializability details just so I can try and hammer everything down because I have brushed over a couple of things. Number one is that, like I mentioned, we don't have a global deadlock detector. What this means is that, again, we're going to lazily remove locks. And so the problem with this is that we are basically prioritizing throughput over latency, right? Because if we had a global deadlock detection system, every single client who was trying to do a write to one of these rows where a lock was left over wouldn't have to do this removal. It could just write to the row. At the same time, it does probably add a lot of complexity to have a centralized system looking for leftover locks and removing them. Another thing is that potentially if we're too eager to remove locks, right? If we see locks and we always remove them because we think, ooh, the client probably went down here, some percentage of the time the client is going to be up. Maybe it's just a long-standing transaction. So Percolator does a few different things in order to try and ensure that we don't erroneously remove locks that are part of active transactions. One of which is going to be, we'll actually put timestamps on locks so that we can see how long it's existed there for. And a client will occasionally update that timestamp as the transaction goes just to ensure that, I'm still alive. And number two is that it'll also attach something known as a chubby record. When it logs on or when a client starts up with Percolator, the first thing that it's going to do is go to Chubby. It's going to get some unique key that it registers in Chubby, and then if it goes down, that key is going to be removed from Chubby automatically, right? Because it's no longer pinging along with Chubby and sending heartbeats. And so another client that sees that lock left over will see the Chubby record associated with the lock. It can then read from Chubby and say, hey, is this thing still there? Is this record still valid? If it is, we know the client is up. And if it's not, the client is probably going to be dead. Cool. So another thing is that every single transaction is assigned a read timestamp, or basically a start timestamp, and a write timestamp. So basically the start timestamp is literally right when you start the transaction before you perform any reads. And the write timestamp is basically right when you have written all of your locks. So right after you finish that prepare phase. So the locks are originally going to be written at the read timestamp. That's the timestamp that all of the locks are written at in Bigtable, and then finally you get assigned a write timestamp because when you remove the writes and commit the data, that is the timestamp that's actually going to be used. Cool. And so all of these timestamps are going to be assigned in monotonically increasing order by something called the timestamp oracle, which we're going to cover in a little bit. Now, a quick note on the timestamps themselves as I start to get sweaty here. Basically, the gist is, let's say I'm reading data, right? I'm some read-only transaction T. If I have the timestamp T, I know that basically any data that I see in Bigtable with a timestamp less than T is going to be data that I'm guaranteed to be able to read, right? So as long as that data has been committed, I'm going to be reading it. There's no chance that I have to do any waiting and be like, if I'm timestamp 20, it's not possible for a write with timestamp 18 to commit after my read is complete. So either the data has already been committed, or the other kind of edge case here is that the data is still being written. However, the idea is we're basically just going to block until they are removed. Because we know that if there is a timestamp less than our read timestamp, like I mentioned, you get assigned your write timestamp after your locks have been written. So when you see locks on a given row that you're reading with a timestamp less than yours, you basically just wait, and then the write will come in eventually. Cool. As far as this timestamp oracle goes, right, this is kind of a central service in the sense that it is literally one service that assigns every single transaction, regardless of client, both a start timestamp and a write timestamp. And that's going to get expensive, right? So we're doing this for all transactions. And in theory, this can easily become a bottleneck. This is another place where Percolator is just like, you know what, I don't really care if I'm sacrificing latency. I'm still getting a fair amount of throughput. So how is it that they're getting a fair amount of throughput with this thing? Well, there are two ways. Like I mentioned, every single node itself has a Percolator process, which is pretty relevant here. This guy right here, the Percolator worker. And so that Percolator worker is going to be handling many transactions at once. And as a result of handling many transactions at once, Sorry, I'm still trying to find my slide again. Here we are. As a result of trying to handle many transactions at once, we can just go ahead and batch those requests to get a timestamp for each of them at a time. That way we can limit the number of RPC requests that we're making to our timestamp oracle. Number two is that we are also going to be serving requests from memory. The idea is, let's say I am the timestamp oracle right here, TO. If I'm a client and I'm another client, basically we can serve numbers from memory. And the only one requirement that we have with the timestamp oracle is that if I've served a timestamp number to a client, that I will never serve a lower timestamp number than that ever again. And so all I have to do, if I'm the oracle, is, maybe in the background every 10 minutes, I can say, hey, here's the highest number that I'm going to serve before I reach back out to disk again. So, I'm able to serve numbers 1 through 10 right now. And then let's say, we keep doing this. Eventually we get to number 9. We've served all of that through memory. Now, we got to go ahead and make another write to disk. Let's go ahead and bump this thing to 20. And that way we know that, even if we go right down after, or basically even if the timestamp oracle goes down after assigning 9, it's going to start back up. It's going to read from disk, where disk is probably GFS in this case. And then it's going to say, okay, I'm starting at 20. And that's fine because, again, these are monotonically increasing. They don't have to increase by 1 at a time. They just need to be increasing in general. Cool. The last piece of the puzzle here is something called observers. Now, I think observers is kind of a secondary piece to this paper in the sense that they do it, but I don't really think it's anything that groundbreaking. But I'm still going to cover it because why not? I read the paper, may as well talk about it. So basically, observers are very, very similar to database triggers with the one difference, and I didn't realize this before this paper, that database triggers evidently are run in the same transaction as a write itself, or at least that's what they say in the paper, but their observers are kind of run as separate transactions and are just used to basically follow up writes with other writes. Cool. So, when there's a write to a particular column, if there's an observer registered on that column, it is going to run at some point and handle that write. So the one thing to note is that the observers themselves are run on a column basis. They may batch those operations, but the one thing that Percolator does ensure is that for a given write to a column, we ensure that only one observer, so observers can be run on multiple different threads, only one observer of that kind is going to commit for it, right? So maybe multiple observers are going to run, but only one of them is going to commit the resulting data that it computes. How do we ensure this? Pretty simple. We add 2 extra metadata columns to our data column over here, one called notify and one called acknowledgement. So basically, whenever new data is written, we put an indication in the notify column. Whenever an observer finishes running for a given value, for a given data value, we'll actually put the timestamp that it finishes running in the acknowledgement column. This is basically going to ensure us a couple of things. So let's imagine that we have this write over here, y equals 5, and that was written at t equals 1. Note that we now have an acknowledgement t equals 3, which guarantees us that because t equals 1 was the time of the previous write, that we've already run an observer for that write. So that's pretty simple because we know that whenever we have a read timestamp, t equals 3 in this case, if there's another write with a lower timestamp than that, it means the read has seen it because we discussed those guarantees earlier. So another thing to note is that the nice thing about this acknowledgement column is that not only does it help us ensure that we aren't rerunning on data that we've already ran an observer for, it is also going to allow us to stop concurrent observer runs from both committing. The reason why is that they are going to conflict when trying to write the acknowledgement column. So let's say that 2 observers see that we write this value x equals 10 at t equals 20. They see, ooh, the last time this thing ran was at t equals 6 because they're all scanning the notify column, and they say, ooh, okay, we have another value to run for. The observer for this value has not run since t equals 6, which means it hasn't seen the new data, which means that we have to run it again. So maybe 2 threads are scanning that notify column, and they both try and run observers. They're both going to eventually try and write back over here. Let's say they're running at t equals 25. They're both going to try and write back to the acknowledgement column because of the fact that you need locks in order to do so. One of them is going to conflict with the other, and only one of them is going to win. And as a result, only one of them is going to commit the data. Cool. The last piece of this is if you do remember the big table video that I made This notify column, in order to keep it relatively easy to read, is going to be stored in its own locality group. Its own locality group just means that it's going to be stored in its own column-oriented format, effectively meaning that even if this is a super big table with trillions of rows, there's probably only going to be maybe 1 million new writes that the notify table has that we haven't run an observer on. And so as a result of that, because all the null values can be compressed together, it's really, really easy to scan this thing. It's going to have comparatively quite a few less rows, and it's just going to be quicker to read. So that's a nice little optimization there. Okay, so let's do the conclusion phase of this video, because we're getting there and I'm starting to sweat because the sun is hitting me directly here. So let's talk about Percolator versus MapReduce for Google's actual use case here. If we're using MapReduce, we have to process every document. Covered that piece already, hopefully fairly straightforward. With Percolator, all we have to do is go ahead and process documents incrementally. It comes in, we run the transaction that we need to run, we assign all the locks that we need to assign. We don't have to worry about our invariants changing as we're making that write. That being said, Percolator writes are going to be pretty expensive. We're doing a two-phase commit, we're writing a bunch of locks, we're running a bunch of observers. It takes a lot of RPC calls to do this. Comparatively, a lot more than MapReduce, where effectively we're just doing one write per key because, we'll do our mapper, we'll shuffle the data, we'll do our observer, or our reducer. Geez, I can't speak. So I guess the gist is, ultimately, in the paper, they kind of do an experiment where they look at the percentage of the web index to process at a time versus whether it's worth running Percolator or MapReduce. And ultimately they find that it is very much worth running Percolator until you're processing about 40% of the cluster or more, at which point it still becomes worth running MapReduce again. And so this is ultimately a trade-off that you have to think about, but the reality of the situation is they're really only processing a few documents incrementally at a time, and so Percolator is ultimately a system that is very much worth using. That being said, like I mentioned, there are a lot of things that Percolator does that maybe makes it very nicely tailored for Google's use case, but not too nicely tailored for general use cases, right? They really prioritize throughput over latency, and ultimately that means they cut a lot of quarters. This kind of timestamp Oracle concept where you just have one central system and it's just like, flicking out timestamps as fast as possible. It's an interesting one, but in reality, I don't know how well it would work, and it certainly can't scale infinitely, right? You're limited to one system at a time. Number two, this piece of lazy lock cleanup. I think it's very cool. The kind of primary lock idea is very interesting, and it's a great way to synchronize. At the same time, if I'm a transaction and I want to write, I don't want to have to clean up other failed transactions. I just want to go ahead and write. They should clean themselves up. Number three is that Bigtable and GFS themselves are not going to get you super low latency. If you recall, GFS in general does basically like this synchronous replication where you have to pipeline your data through all of these guys and then pipeline it back, the acknowledgements, and then you're writing to them again with your acknowledgement orders so that all writes get applied in the same order. It's not fast. And then Bigtable doesn't exactly make that any easier. Though that being said, Bigtable at least does have writes to a mem table because we're doing that kind of LSM tree SS table implementation, which is pretty nice. That being said, who am I to judge? This works for them, right? They wouldn't write the paper otherwise if they weren't getting utility out of this. And that is ultimately what matters. You don't have to boil the ocean. You don't have to build systems that solve every single problem. You're building systems to solve one particular problem, for the most part. And if it does that, then it's a good system. And so for that, I'm going to give the Percolator system credit. Now you may note that it's obviously not a household name because evidently it's not that general. I am very curious to know if they still do use this type of thing at Google. I'm going to wager to say no because it's been 14 years, but who knows. Anyways, guys, I hope this video was interesting. Hope you enjoyed it, and I'll see you in the next one.